We're now about to get into some really cool group theory and something that's really powerful for cube solving algorithms. One of the ways that many algorithms go is you work with different combinations of these 6 basic motions until you find one that accomplishes something special or interesting. And often what I mean by that is something that will keep most of the cube intact while just moving a couple of pieces around, just moving a couple of cubies. And that becomes some kind of special motion. And then what we really want to do is use that trick of if I perform this sequence of moves, I'll just be moving these very few cubies around, and we want to try and expand that trick as much as we possibly can. And the clever method for using that trick for all it's worth is something called conjugates. So the general philosophy of what a conjugate of a motion is suppose that x is this move, could be a sequence of these more basic moves that we've described so far, but suppose that x is some sort of move that does something desirable. For example, maybe it swaps two very specific cubies. Then what a conjugate of x is going to do is it's going to have this feel of being three-parted, and it's going to do something really similar to x. For example, if x is something that switches two specific cubies, then maybe this conjugate of x will switch to different cubies, but it has this particular three-part pattern. The first part of the pattern is we're going to do a different motion of the cube to get the cubies we want switched into position for x. Then we're going to perform this move x where we know very well what it does. And then what we're going to do is invert the motion we did to get into position. So it has this feel of put some things into place, do the move that we know and love, and then put them back. If we want to be very specific and formal about it, let's suppose that x and y are moves, maybe elaborate moves, sequences of moves, whatever, on a Rubik's Cube. Then the conjugate of x by y is the combination of the moves, first y, then x, then y prime, where y prime is denoting the inverse of y. So we're going to do an example that's going to walk through a motion and its conjugate, and what the conjugate does might seem random at first, but we're going to do is walk through it slowly and see if I can point out the ways in which we actually find that it is similar to the original motion after all. So what I'd like to do is look at the motion x, which is a nice simple motion. Let's have it be u prime. And then for the y, the thing that we're doing and then undoing later on, let's use r as an example. So our original motion is u primed, and our conjugate motion is r, u primed, r prime, which I've visualized below. First we do r, then we do u primed, and then we do r primed. And when I take a look, even though we've only done 3 motions on the Rubik's Cube, when I take a look at this image, it already looks pretty screwed up to me. But what I'd like to walk you through is that I think that it's actually fairly understandably mixed up, and I want to convince you that it's not so different from u primed after all. So let's take a look at that original state of the cube, and let's think about what u prime does. It takes this upper level of the Rubik's Cube and it rotates it once counterclockwise. As we've seen before, everything on the bottom layer is entirely stagnant for that motion. It doesn't move at all. So in particular, if we had any cubies on this cube that are not involved in the motion u primed and they're not in the motion r, then they definitely won't be involved in the motion for r primed, and those cubies will be stagnant throughout the entire sequence of moves. So those cubies should not move at all. So if we're looking at cubies that are not involved in u and not involved in r, this cubie right here is not involved in that, and this back cubie that you can't really see, but I've shaded in purple over here, is also not involved in either of those motions. So those 2 cubes should stay still throughout this whole sequence of moves. Next, I'd like us to think about things that are not involved in the U-primed motion, which is again the bottom layer of the cube. If I have something in R that gets moved into the bottom layer of the Rubik's Cube, then that piece will stay put while the U-prime motion is performed. And I will immediately then perform R prime, which takes everybody, which undoes the action of R. So the action of R was moving that cubie down into the bottom layer. The U prime didn't affect that cubie. The R primed action puts it back. So anything that is moved by the R action into the bottom layer is going to go right back where it came from and stay fixed in this whole composition of motions. So in particular, this is one of those pieces because when I perform the R motion, it'll move over to here. The U prime motion will leave it alone and it'll move right back. And this piece right here, because although it's in the upper layer right now, I first do the R motion, which moves it to the bottom. I then perform the U prime motion, and then at last I move it back to where it came from. So these 4 squares, these 4 cubies that I have highlighted, should remain fixed throughout this whole series of motions, and the 4 remaining cubies should move. And if you take a look at the original, and the original with those stagnant cubies shaded in, and then the R, U primed, R primed, you'll see that the cubies that stay put, I have a green, yellow, orange cubie, green, yellow, orange cubie. I've also got this one back here, this white, red, and blue cubie that stays exactly where it is. You can take a look and compare and notice that those 4 cubies do actually stay put. And so the 4 cubies that are moving are here, 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 and here. And those do not match with their picture over here, while the other 4 do. So while U primed was a simple rotation of a face of the cubie, R, U primed, R primed, this conjugate, doesn't move a face, but it does move 4 cubies, just like a rotation of a face might do. And what's more, if you take a look at the cycle structure of both U primed and R, U primed, R primed, you'll notice that the cycle structure is exactly the same. And so the order of this U primed is 4, and the order of this conjugate is 4. So here we have 2 different motions of the Rubik's Cube, both of which have order 4, and take 4 cubies and cycle them around with one another, leaving 4 other cubies entirely stagnant. And so in that sense, we have a real similarity between the U primed and the R, U primed, R primed.